I'm Ross Bagurtis, and in this video, we're going to be discussing network models. Now, if you know anything about networking models, you'll realize quickly that they can be boring, and they can be laborious and academic and not have any value at all. And I will fight tooth and nail to disagree with you on this topic consistently. The CCNA is going to test you extensively on your knowledge of what protocols fit within which layer of a model, and it will also help you in the future to understand where protocols operate in the organization of how we send data across a data network. Let's dive in and take this non-academic approach to a very academic topic. We've already seen this. Network protocols, they're all over the place, and we have lots of them. Now, in the introduction to network protocols video, we took a look at some of these application-like protocols that we use on a regular basis, like HTTP and HTTPS, DNS. We took a look at some that we don't use so often, like FTP and Telnet and SSH. And we also took a look at some email protocols like POP3 and IMAP. But in the world of data networking, there are lots more protocols to get this all to fit together and work properly. And those can include things like IP, Cat6 cabling, T1s, TCP, UDP, ICMP, SNMP, and there are a multitude of other protocols on here, both current and deprecated, that we use constantly in data networking. Well, we of course don't use the deprecated protocols, but we have a whole mess of protocols that we use consistently. So let's take a look at how we start to organize this. So the OSI model stands for Open Systems Interconnect, and it is an open model, meaning anybody can use it. It's designed by ISO, the International Organization for Standardization, and ISO actually means the same in Greek. So ISO developed this model so that network engineers across the world could have a similar mechanism to implement in order to get two devices to communicate with each other. And what we've done is we've created categories, and these categories, they show up as layers of this model. So layer 7 is always our application layer. And we work our way down. 6 presentation, 5 session, 4 transport, 3 network, 2 data link, 1 physical. And those numbers are always associated with the layer that we're discussing. So physical layer is always 1. Application layer is always 7. However, this model has reached a point in its history where we don't often use some of the layers of this model, and we actually just eliminate them. So they don't actually have a purpose anymore like they once did. And we can oftentimes get confusion in there because of this, and a lot of people find that this confusion that we're creating in the OSI model, because we don't use 2 of the layers, can actually hinder them from using it successfully in data networking. And I'll tell you right now, we absolutely have to have this in order to understand the basics and the details of data networking. So let's make this practical. The first thing I'm going to do is eliminate the 2 layers that we don't use anymore, and that's the presentation and session layer. So we don't use those. We're not even going to discuss them through the rest of the video because they are not used. There was a point in time when we needed a presentation layer. That was because computers used to only speak in a certain type of encoded text, and the standard for that was called ASCII, ASCII. And IBM then came out with another protocol called EBCDIC, EBCIDIC. I think I spelled that wrong, but it's something like that. EBCDIC, EBCDIC. And they're essentially the same exact thing. They both had the same text they were trying to transfer. One just encoded the text in EBCDIC, and the other encoded the text in ASCII. Well, at that time in the 70s, when this was going on, network engineers needed a protocol in order to translate the ASCII to EBCDIC and EBCDIC to ASCII in order to get the 2 devices to talk. Well, that was mainly because IBM developed this proprietary encoding of text, and we had to have a mechanism in order to talk back and forth with these devices on a data network. Presentation layer was a perfect spot to do this. But we don't use the presentation layer anymore because we've pretty much standardized how we encode text across a data network as ASCII, or we just create a file system in like Microsoft Word and create a document and find some other mechanism to translate it. We don't use the presentation layer anymore. The presentation layer was also designed to have encryption protocols occur at it. However, we've really pushed those to other layers of the OSI model, namely the network layer and above the application layer, beyond the application layer, within applications themselves. The session layer was used heavily in the past for an old kind of firewall called SOCKS, which was a way that we could redirect traffic at the session layer to another device that could act as a proxy for us. We also used to use it in Microsoft Remote Procedure Call protocol, which was used in older Microsoft client-server applications. NetBIOS, another protocol, was used at the session layer, which is a Windows systems feature as for older systems as well, and we don't use that anymore. So although we have these two layers in the model, they do have a purpose. We just don't use them much anymore. So let's eliminate and not even talk about those two layers of the OSI model now, and we'll make the rest of this very easy so you can see exactly where all of our protocols fit into the system and see how they work. There's a problem though. The problem is that there are other network models out there. This one is the TCP/IP model, which was developed from the Department of Defense model. And if you look at this model is actually pretty slick. It mirrors very much the OSI model, but only the usable portions of it. If we put them side by side, we'll see that the application, presentation, and session layer of the OSI model match up directly with the application layer of the TCP/IP model. We don't use the presentation and session layer of the OSI model, so because we don't use those two layers, we cross them off. The application layer in the OSI model looks very similar to the application layer in the TCP/IP model. The transport layer is the same in both. The network layer is the same in both. And then at the data link layer and physical layer, the TCP/IP model combines those into one layer, the network interface layer, and we break it up into two layers in the OSI model. What's the big deal here? All we're doing here is we're separating the data link functionality from the physical functionality. Another way to say this, the cabling functionality we're separating from the network interface card functionality at the data link layer. Since the network interface card in our workstation oftentimes requires a specific cable to plug into it, like an Ethernet cable or fiber optic cable, these two layers of the OSI model actually go hand in hand usually, and the TCP/IP model combines them into one. Now the question is, which one do we use? We unfortunately use the OSI model and eliminate the presentation and session layers, and we leave the TCP/IP model as kind of an academic concept that people who are designing TCP/IP applications and protocols may use this format to describe what they're doing. Either format is correct, but in data networking, as network engineers, you're going to be using terminology like layer 1 problem, layer 2 problem, layer 3 problem, and so on. So let's take a look now at what each layer is doing and what protocols operate there. We'll start up at layer 7. Layer 7 is the application layer. At the application layer, we have protocols used by servers. So the application layer is not the application itself. So at the application layer, we'll have protocols like HTTP and HTTPS, Telnet, SSH, FTP, SFTP, TFTP, POP3, IMAP, SMTP, DNS, etc. Now in the Introduction to Network Protocols video, these are the exact protocols we took a look at. And the reason we took a look at these protocols is because as an end user new to networking, you are most familiar with using these protocols to surf the web, especially HTTP and HTTPS. Now we may want to think that our browser, like Internet Explorer or Chrome or Safari or Firefox or Opera, or I'm sure there's others out there that you've used, or maybe not, all those applications, those browsers or applications that make use of an application layer protocol like HTTP or HTTPS. So we can use Google Chrome, Firefox, or Internet Explorer and all browse to google.com or trainsignal.com and have a similar experience in every single browser because each of those browsers implements the HTTP protocol. This is true with the other protocols as well. SSH and Telnet, we use an application like PuTTY, or if we're on a Unix system, Telnet and SSH are built in natively to the operating system. FTP, SFTP, TFTP, there are applications we can download like FileZilla as an FTP server or an FTP client, and that will actually make that FTP application work. And there's a multitude of those out there as well. Same thing with email and DNS. So our application layer really is designed to host protocols that are used by servers and by applications in order to pass traffic across a data network. Layer 4 is the transport layer. Here's where we're going to do something called session control. And to do session control, we're going to use two protocols, TCP and UDP. TCP is Transmission Control Protocol, and UDP is User Datagram Protocol. Of all the protocols in data networking and all the layers of the OSI model, the transport layer is one of the more complicated layers to understand. In addition, it's the one where all the meat and potatoes are happening, especially with respect to using firewalls. So we often consider firewalls a transport layer device. And the firewalls can monitor the TCP and UDP protocols to see if any naughty stuff is happening. The idea of the transport layer is this. Transport layer sets up a session between two devices. Now this is best explained with an analogy between two people making a phone call. So if I want to make a phone call to my friend, and I'm using a landline phone, I know that's a bit archaic, but let's just pretend for a moment that we have landline phones again. Some of you probably do. Some of you may not. Doesn't make a difference. At any rate, if I wanted to call my buddy and have a conversation with him, I can't just pick up the telephone and start talking to him. Because if I pick up the telephone and start talking to him, nothing's going to happen because my buddy has no idea that I'm trying to send him a message. So in order to tell my buddy that I'm trying to send him a message, what I have to do is I have to go through a very specific process. And the process is the same for everybody using a telephone worldwide pretty much. And that process goes like this. We pick up a phone. We listen for the dial tone. Once there's a dial tone, we dial a phone number. After we dial the phone number, we wait for the phone to ring. The phone rings and rings and rings. Once our buddy answers the phone, he says, hello. I say, hello. Once that process is complete, now, and only now, I can begin talking with my buddy. So what I have to do is I have to actually build up a connection between the two endpoints before I can transfer the data. And that's exactly what TCP does, is it establishes a connection between the two endpoints so that data can be transferred reliably and successfully between them. And we're going to take a look at this in a lot more detail in a future video because TCP is such a critically important protocol in running networks. And if you notice there at the transport layer, there's only two protocols we're going to use, TCP or UDP. And we're going to also find out that each one of these application layer protocols up here is going to make use of either TCP or UDP when it communicates. So all these application layer protocols are designed to work with either TCP or UDP. Let's go down to the network layer. Network layer, layer 3, the network layer is responsible for the delivery of individual packets. There's the big protocol that operates at the network layer, and it's really only one, and that is IP. And we're currently using IP version 4 with some smattering of IP version 6. ICMP, which I've listed here, is called Internet Control Message Protocol. That's a sub-protocol of IP, and we use ICMP very, very often, especially with a utility called ping. Ping is a packet internet groper. Yes, I know, groper, that is actually what they called it. You'll find throughout the CCNA training series that network engineers have a wicked sense of humor that can be a little dirty at times. So we have at the network layer, the primary protocol is Internet Protocol. And then we have the secondary one, ICMP, which we use for ping. Now, Internet Protocol works much like the post office, and it has very similar responsibilities. So the Internet Protocol is responsible for logically addressing every device in an internetwork with a unique address that has a logical hierarchy to reach it. So we can compare that exactly to how the post office does business. Now, if we think about the post office gives every single residence, business, or basically a room that can accept mail, it gives each of those locations an address. And that address is composed of several components. But the big components in it are the street address and street name and a zip code. So if we think about the zip code represents a whole bunch of residences and businesses. And inside that zip code, we have individual homes and businesses, and each one of those businesses and homes has a unique street address with a house number and street name. And through this mechanism, we can send a letter from anywhere in the United States to anywhere else in the United States by simply using two pieces of information, the zip code and the street address. The zip code tells it generally where it needs to be, and the street address tells it exactly where it needs to be. We go further and identify a unique individual inside of that residence, but I'll come back to that in a second. So what the network layer does with IP then is IP creates a logical addressing scheme that divides devices on a network into groups of devices called IP networks, and then hosts on the individual hosts then on the IP network. Let's give an example. In your home network, you have maybe a laptop and a tablet. Now those are two devices, and they're both on the same network. They're both inside of your home, connected to the same wireless access point. They're both on the same network. As opposed to Google, Google's on a completely different network because Google lives out on the public internet and it's not in your home. Google is out on the internet and is a device someplace else. So with IP, what we do is we give each device a network identity, and then we give each device a host identity. And what that does then is it then uniquely identifies every device on the internet and gives a system of organizing that data in a hierarchical pattern so that we can reach all the devices on this internetwork of devices. Same way the post office does it. As a matter of fact, when we send packets at the network layer, we actually put them in a virtual envelope and we address them with the source address, the sender's address, and the destination address, the receiver's address, much like we do with the post office. The network layer is also responsible for actually routing the individual packets across the network. So what we're going to see is the transport layer is going to break up large chunks of data at layer 4, and it's going to send it down to the network layer, and the network layer is going to take those smaller chunks of data and send them out individually, and it has mechanisms built in through routing protocols to allow the packet to get from its source to its destination and back again. So the network layer is really responsible for moving the traffic across the internet. So far we have application layer, where we have protocols that actual applications will use. We have the transport layer, which builds up the connection between two endpoints so that data can be transferred. We have the network layer, which is responsible for addressing and moving individual packets. That brings us down to layer 2, the data link layer. Now the data link layer represents connections between devices themselves. There's lots of protocols that operate here, and they're constantly evolving and changing as the technology changes. Ethernet is probably the most popular layer 2 technology, and Ethernet comes in multiple forms as I've listed here. We have wired Ethernet, which is typically just called Ethernet, and then we have wireless Ethernet. And inside of wireless Ethernet, we know that the standards keep changing. We've seen this happen over the last 10 years. We went from the wireless Ethernet 802.11a protocol, and then we introduced the less expensive 802.11b. And then we wanted faster, so they came up with 802.11g, and they gave us faster speeds. Then we wanted faster, so they came up with 802.11n, and that still wasn't fast enough for us. So now we have 802.11.ac. So these protocols for wireless Ethernet and Ethernet are data link layer protocols. There are other protocols that operate here that you may not be as familiar with. Something like a serial connection, which is often called a T1, or if it's a faster one, a T3. We have asynchronous transfer mode, or ATM, is another mechanism of transferring data between devices. DOCSIS, D-O-C-S-Y-S. This is a protocol that your cable modem will use to transfer information from your local network out to the cable company who's providing you internet access. There are lots of other data link layer connections here. Now, the data link layer has its own addressing scheme as well. And the addressing scheme at the data link layer is a physical address. Now, that physical address is actually burned onto the hardware when it leaves the manufacturer. So it's actually given basically a serial number from the manufacturer that's burned onto the device. This is often called a MAC address if we're using Ethernet. It can be called a hardware address or physical address as well. Now, up at the network layer, we had a way of addressing individual networks and individual devices on each of those networks using the IP address. And that was a very logically organized system. The data link layer, on the other hand, MAC addresses, although they do have some organization, you can identify who manufactured the particular network interface card that you're using with the MAC address. But other than that, we don't have much information about where a device is on Earth based on the MAC address or the hardware address alone. The way I look at this is kind of like a social security number in the United States. Now, in the United States, every human being, for the most part, unless you're trying to cheat the system, every human being is assigned a social security number, and that number is unique to you. It has some identifying information in it, like either where you were born or where you were living when you obtained it, or if you're an immigrant and you receive the number. You can tell based on the number how it was assigned to you, but that's about it. My point to this is, if we go back to our post office example, is that I can live in the house I'm in now with a specific post office address in a zip code with a house number, or I can go move someplace else. I can go move across the country. Right now I live in Madison, Wisconsin. I could go move to California. I could move to Chicago. I could move to New York. My social security number would not change, but my zip code and home address would change. So this is in the same way that it works in a data network. The MAC address is unique to the device. It does not change. And as we move our device from one network to another network, let's say we move our laptop from our home network to our work network, what we're going to see is that the MAC address of our device stays the same, but the IP address that our device obtains is different. And in this way, we've basically moved our device, the social security number of our device, we've moved it from one network to another network. The social security number, the MAC address, has not changed, yet the layer 3 information has. And it's this fundamental concept right here of having a unique identifier at the network layer and a unique identifier at the data link layer that actually make data networks work very, very, very efficiently. And in CCNA, we end up spending a lot of time talking about the interaction between layer 3 and layer 2 because it's a very important interaction, and we're going to take a lot of time to understand this as well as we can. Once we get down to layer 1 now, the physical layer, this is where we have one of 3 options to move data. We can either do it with photons via wireless. Now, photons, somebody could argue with me and say that, no, 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 we're sending them over radio waves, and yes, you would be correct too, and I would also be correct in saying they're photons. Anyway, wireless is using radio waves or photons to transfer data. We can use glass as our medium at the physical layer. In glass, we use fiber optics. Fiber optics we can use to transfer large quantities of data very reliably over very long distances. Last, we can use copper wires or any metal for that matter. These often come in forms of Cat5 or Cat6 cabling. In fiber optics, we have single mode and multi-mode fiber. And in wireless, we have multiple options in wireless for how we can transfer the data. Both the 802.11 series of protocols for wireless, as well as some proprietary versions of wireless that we use in larger enterprises to connect buildings together. So this boils down the most practical version of the OSI model and what happens at each layer. Let's take a step next and look at the addressing at each layer. So the addressing at each layer of the OSI model works like this. At layer 7, at the application layer, we really don't worry about addressing at this layer. If there is any addressing happening, it's happening with the application itself or inside the protocol. We typically, as network engineers, don't care about this. We leave this to our web designers or FTP administrators or other application analysts in our network. We usually let them worry about what's happening with the application and the application layer. Because remember, those are the protocols that run on servers and are used by applications. Now at the transport layer. The transport layer, we're going to use an addressing scheme called port numbers. The port numbers can be between 1 and 65,535, and the first 1,023 port numbers are reserved for well-known protocols. We've already talked about some of these well-known protocols like HTTP, HTTPS, FTP, SFTP, TFTP, and so on. And we'll take a look at what those protocol numbers are as we move through the course, because it's going to be very important that you begin to memorize which port numbers belong to which application layer protocol. At the network layer, I've already talked about this a bit in the previous slide. We use IP addressing, Internet Protocol addressing. Those addresses are divided into two components, the network portion and the host portion, and we use those to give every single device on the internet a unique identifier so we can logically route traffic to and from it. At the data link layer, we have the MAC address if we're using Ethernet, and there are other layer 2 addressing schemes like a DELCI number or data link connection identifier number if we're using an old school protocol like frame relay. Most often at the data link layer, we're going to see the MAC address. And once again, that MAC address is kind of like that social security number that you're assigned in the United States as your tax ID number, as a unique identifier of you as an individual in a big system. The physical layer is pretty dumb in this respect. It has no addressing. We have to have the cable set up in an appropriate fashion in order for it to work, but we don't actually do addressing at this layer. So this wraps up the beginning of the conversation about networking models, and what I attempted to do here was break down the OSI model into only its bare bones pieces that we use in data networking in modern networks. Now there's still more to understand about the OSI model, so we're going to need to continue on this conversation and talk about how encapsulation works using this OSI model. And what we're going to find out is we're going to put all these pieces together and look at the port numbers, IP addressing, layer 2 addressing, and how they all fit together and actually are able to create a system where we can transfer data from one device on a data network to another device on the data network. Thanks for taking a look at this video, and I look forward to seeing you in future videos. Thank you.